Skipper on this one for starting late. He was still logged in, so I had to reboot the computer. That's okay.
It's good.
Oh, I was also running a little late today. Just glad I'm almost done with all of this school board crap. Alright, so so I think people will start joining us. And we were at the school board on Monday, and this was a meeting where they had 2 hours discussion about renaming Lee Middle School. Public comments. You can just watch the YouTube video of it. Just watch it. All right, so we're working with probabilities. All right. So we're gonna just kind of review what we learned, and then we have these examples. But before we do that, so the exam, get your exams. The grade for the quiz part.
The theoretical.
Yeah, the theoretical part. So that grade is now what you have. That is your grade. It's in there. So I went through. The only ones I really had to check were the fill in the blank ones, the rounding. Just remember our rounding rules. So if our target is greater than, so if the digit after our target is greater than 5, we round up. If there's nothing, we leave it the same. If it's 5, then we have to go to that next digit. So if there's nothing after that 5, or if it's a 0, we leave it alone. Right. If it is 5 and something follows it, like a 1 or a 2 or a 3 or 4, then we go up. So our idea is that if we have a 5 and it's just strictly the 5, we're going to leave the digit as is. But if it's a little bit more than that 5, we're going to round up. So not many people had that. I think. So check it out. I went through. I just had to correct a couple scoring, a couple scores, but that's set. I'm gonna have to go through and look at the R stuff, and I'll get those grades set. I'll get those grades updated. I don't know if you get notified as soon as I hit the submit button after I add your comments, or when I finish grading all of them. I don't know. But once I do, what you'll see is I'll upload a key as a PDF that you can then see what your answers are. And I'll also unlock the actual exam itself that was on Blackboard, so you can see the questions, you can see what the answers were, what you can see what you got wrong, what you were expecting, and so forth. So I'll get those updated. I think it worked out okay. Only had a few questions about some of the R stuff, things not knitting or not working properly. So I come to expect that. I think we end up having fewer of those problems as we move forward. All right, so working with probabilities. Cursor. All right, so we've introduced the addition rule. If two events, A and B, are mutually exclusive, all right, then the probability of one or the other is the sum of the two probabilities. All right, so mutually exclusive means the events cannot occur. All right, so they cannot occur. If our events, so we defined it mutually exclusive, right? And we compared non-mutually exclusive. We'll show you how to do those in a bit. The other part is if our two events are independent and not mutually exclusive, then the probability that both occur, that they occur together at the same time, is the product of their individual probabilities. And we can expand it out to however many events we're looking at. All right. If we are interested in the probability of A or B occurring, and these events are independent and not mutually exclusive, then it is the sum of our two probabilities minus the union of our probabilities, or minus probability that both occurred together. So we went over and said that reason is that probability of A includes this slice, probability of B includes this slice. So if we do A or B and add our probabilities together, we have two of these slices. We only want one, so we have to subtract one of those out. Oops, I didn't see that. Maybe they thought kind of, there's their slice. All right, so then we expand the multiplication rule, and our examples are genetics. All right, so I asked you to do like Punnett square, come up with these probabilities. So what did you get for the probability of big A, little a? What was it? 1/2? Okay. How'd you get that? Because it's known, right? Yeah. It's known. So easy one is recognize our Punnett square. So each parent gives an allele. Probably see that. Each parent gives one allele. Which allele gets given is random. So each one is random. So when we look at the possible combinations of those that are being given, we get 2 of these big A, little a's. So we got 2 of those outcomes out of a total of 4 different possibilities, which gives us 1/2. Pretty easy, right? Pretty easy. All right, so I'm going to apologize to the people on the live stream. We are going to move this camera over to our board. And what we're going to do is look over that probability. So, move this. I don't know my edges. We'll make it work. All right, so that first probability, we did the Punnett square. All right, so we had our big A, little a times big A, little a. We did our Punnett square to figure out what the probability is of that big A, little a. Can we do the same thing using our probability laws? Probability, yes. All right. So this parent is going to give either big A or little a. Right? It's going to give big A or little a. It gives it at 50-50. So half of the time it gives a big A, half of the time it gives a little a. This one is going to give either a big A or a little a. And like the first one, we have a 50-50 chance of getting. So it'll either be 1/2 big A, half the time it'll be little a. Now we're asking for big A, little a. That's what we're asking. So where does it come from? Well, we can have this. We can give big A there, and then what must we have? What has to happen if this parent gives big A? The other one has to give little a. So this one is big A from parent 1. And if both events have to occur together, so are they independent? Yes. What happens with the parents, with the gametes, are independent of each other, right? Are they mutually exclusive? No. All right. We can get a big A and we can get a little a together. We can get a big A and this big A together. These are mutually exclusive. You can't have one parent give both a big A and a little a. These are mutually exclusive, but taken together, these events
are not mutually exclusive. So these are independent, non-mutually exclusive events. Parent 1 gives big A. Parent 2 has to give little a. So our probability that we get this is equal to our product of our independent probabilities. So that's 1/4. But that's not the only way. We also have to figure out that this parent can also give a big A. So now we have parent 2 giving that big A. If parent 2 gives the big A, then parent 1 has to give that little a. So, independent, not mutually exclusive, we use our product rule, we get 1/4. Now, it comes back to our probability rules again. So, we can get either parent 1 giving our big A, or parent 2 giving our big A. Are these mutually exclusive? Yeah, we can't have our parents can't have our offspring have both of these together. All right? So, if this case was 1/2, and this, 1/4, and this case was 1/4, what do? We add them together, which gives us 2/4 or 1/2. All right? Same thing with Punnett squared. Punnett square is introduced because it's a whole lot easier to kind of understand. We're presenting it as a probability to kind of get you in that probability thing. Questions? All right, so erase that. Let's go to our second one. Second one is big A, little b, little b, times our big A, little a, and big B, little a. We are asking for the probability of getting a big A, little b. All right, so we'll say this is parent number 1, this is parent number 2. All right, so our individual gametes, are they independent? Yes. What each parent gives is going to be independent of each other. Right? What one parent gives has no effect on what the other parents give. Right? Within the games, we have independent assortment, right? So if we have an A, big A, it doesn't affect the probability of getting any of the B's, whatever B we get. Right? So big A, little b, little b. That's our target. So we can have parent 1 give our big A. And if parent 1 gives our big A, what does parent 2 have? Our little a, right? Parent 1 is going to give a little b. Parent 1 gives a little b, what does parent 2 have to give? Also, a little bit. Right? What are the probabilities? A1, we've got 50-50 that we get that. A2 is also 50-50. What about B1? It's 100% probability we're giving that little b. Oh yeah, that's big. And then little b2, 1/2. All right. So all of these events have to happen. We have to have a big A. We have to have a little a. We have to have a little b. We have to have a little b. We have to have that. It's our multiplication rule. We're going to multiply it right across. So we get 1/8 for that. But this isn't the only way that this can happen. All right? We can also have our parent 2 give that big A. And then our parent 1 gives the little a. And then we have our parents both give the little b's. So we have 1/2 1/2. Little b is 1, and then 1/2 again. Multiply across, we get our 1/8. Either of these can occur. So it's either we get our genotype this way, or we get our genotype this way. So we have our addition rule, which gives us our 1 probability. Is that what you calculated? The Punnett square? Did you calculate Punnett square? Punnett squares. So parent 1, those are the gametes that get produced. At probability each. Parent 2 is going to produce a big A, big B, a little a, big B, a big A, little b, and a little a, little b. Yep. So then we have big A, big A, big B, B. How many outcomes do we have? One and four. How do I get those 1 and 4s? Well, we only had 2 possibilities, so that was 2. So each one was 1 out of 2. Here we had 4 possibilities, so each one was 1 out of 4. If we assume independent assortment, right? Segregation, we get those probabilities. Right? So how many outcomes do we possibly have? We have 8 total. How many of them match what we're looking for? There. There. So the Punnett square matches how we did it. Right? Now there's another way to do it. And that's using a probability tree. Right? So the probability tree is kind of like a mix of our methods. So what we do, should have left that here. So we are looking for, those. So with the probability tree, what we're going to do is kind of go step by step to look at our outcomes. So our very first outcome, we're going to look at this parent. That parent can give either a big A or a little a. Right? And each one occurs 50% chance. All right? Then our parent can give the little b. Right? No option. And I put my probability on our branch. And then we look at parent 2. It can give either a big A or a little a. So now what we have are these 2 possibilities on our tree. And each of them occurs 50% probability. Right? And then each of these is going to give either a big B or a little b. And on this tree, I will add probability to our branches. All right. And then what we do is read across the tree along all of our branch points to look at our final genotype. So I'm just kind of going right along our branches. have those, how do we get our probabilities? Think of the tree as a series of decision points. In order to get the end, we had to take that point. We had to take that path. So in order to take that path, all of our probabilities are going to be multiplied. So what we do is multiply each of our probabilities along that path. So 1/2 times 1 times half times half. And that gives us 1/8. All right? We could do it for all of them, but we're only interested in this. So the ones that we want to calculate are here and here. So we have 1/2, 1, 1/2, and 1/2. Here we have 1/2, and 1/2, 1/2. Each of those gives 1/8. Those are two outcomes. Together, it's 2/8 or 1/4. All right. I use this simple probability because it ends up being 1 or 1/2. That's our range point. But we'll get to the spots where our traits, our characteristics, where the probability of the event depends on something else. And these probability trees and putting down the correct probability in each branch will help us calculate the outcomes that we're looking for. All right? All right. Let's see if we have any questions. Say no. All right, so example problems. We have fish in a stream. And these are different than our genotypes, all right, our genetics, because our genetics are a lot of, 1/2 chance that you get the correct game, all right, or it's 100% because you only produce one allele. Right, so here's our example. We're going to work with fish in a stream. Right, 75% of the fish are female, 25% of the fish are male. If we look at the species, 50% of our mosquito fish, 50% of our fish are mosquito fish, 30% are shiners, 20% are darters. Right? So calculate the probabilities. If we catch one fish, then what is the probability that we get a shiner or a darter? Second one, if we catch one fish, then what's the probability that it will be a male fish or a shiner? If we catch one fish, then what's the probability that we catch a female and either a mosquito fish or a darter? If we catch 3 fish, then what's the probability that they're all male? And if we catch 4 fish, then what's the probability that we don't catch a single shiner? All right? We're going to use our addition rules, our multiplication rules. We've got a mix of independent, mutually exclusive, and independent, non-mutually exclusive. All right? We will assume that in our fish, 50% mosquito fish, it is broken down as 75% female, 25% male. If it's shiners, 75% female, 25% male. So that way we don't have non-independence in our ratios. All right? So calculate these probabilities. And then what we'll do is we will review them. Leave that up there, and I'm going to write this stuff up on the board.
So since we don't know which proportion of each fish is male and female, are we going to assume it's just 75-25 for each? Okay.
Yeah, so we assume
They could be skewed.
Yeah, we're going to assume they're independent.
Okay, thank you.
Do we put the fish back after catching? Yeah, I think this group will be put back after catching. I think I have some infections coming up, so we won't put those fish back. All right, how's it going? Let's work through a couple of these. Brand new. All right, so probability of shiner or darker. So the first thing we should look at, so independence will be given to you in the problem. So assume they are independent. Are they mutually exclusive? Yes. All right, so these two, we assume independence. Right, so the probability of being a male does not affect whether that female was a specific girl. Being a male does not affect if you are a mosquito, fish, shiner, or darter. Being a female does not. If we are one of these, we are a shiner, it does not affect the chances that we are a male or a female. Right? So they are independent. We'll get to the non-independent probably tomorrow. Right. Within each of these, there and there, these are mutually exclusive. Mutually exclusive. Because we can't be both male and female. Can't be both mosquito, fish, shiner, and darter together. We're not talking about ligers. So, shiner or darter, is this a mutually exclusive event? Yes. All right. So how do we calculate our probability? If they are mutually exclusive, then this probability of S or D, is equal to the sum of their individual probabilities. So the probability of being a shiner
plus the probability of being a darter, which is 0.3, that's our shiner, plus 0.2, that's for our darter, and thus we get 0.5 for that probability. All right, what's the probability of being a male or a shiner? First up, are these mutually exclusive? No, we can be both a male and a shiner. Right? So how do we do our probabilities? Well, we have or, that is going to imply addition. But does this give us our correct probability? No. We've double counted, so we have to subtract the probability that we are a shiner and we're male. All right? So, probability male 0.25. Probability of being a shiner is 0.3. Then we have to subtract the product. And that comes up with, what's that?
475.
475. You gotta remember the mutually exclusive events. All right, probability of male and mosquito fish or darter. For those who need clarity, this is the probability of male times the probability of shot. Since we have the and. And implies multiplication or implies addition. Right? In this problem, we have two. We've got and or. Okay, both. So, what is this probability? We have to be female. We have to be female, regardless of our fish. So what we're going to do is multiply that by the probability that we're a mosquito fish, plus the probability that we are a darter. So our possibilities here is that we can be a female and a mosquito fish, or we can be a female and a darter. So this is our distributive that you learned in algebra. So I just reword it mathematically. So for this, probability of being a female is 0.75 times mosquito fish is 0.5 plus 0.2. 0.7 times 0.75 is 525. All right. Number 4. We have 3 fish. What's the probability that all of them are female? Or all of them are male? Right? So our first one has to be male. Our second one has to be male. Our third one has to be male. There's only one way to do that. All male. So we have to be first fish is male and second fish is male and third fish is male. Multiplication, 25% chance. One fourth is 1/64. 0.0156. That you guys? Is that right? All right. Last, we have 4 fish. What's the probability that you don't get any sharks? Oh yeah, steel. Yeah. we do that? So here's the thing. All right, we can't have any mosquito fish. And we have 4 fish. So that first fish can't be a mosquito fish. That second fish can't be a mosquito fish. That third fish can't be a mosquito fish. And that fourth fish can't be a mosquito fish. So what I'm going to say is we have that first fish, it's not N. It's not a mosquito fish for a second. And it's not a mosquito fish for a third. And it's not a mosquito fish for your third. So how do we get that? A mosquito fish. Right? You have mosquito fish.
Yeah,
That's
yeah,
a shiner.
It says mosquito fish on.
Yeah,
Oh,
yeah, I read it online.
Jeez, oh man.
Give me a minute.
What's this world coming to? Alright. Well, substitute. Depends on what presentation you have. Alright? Maybe I changed that. I don't know. Alright, so either one. How do we get this not version? 1 minus the probability. So that's kind of one of our rules. Okay? So our total probability has to sum to 1. Probability yes plus the probability no is going to equal 1. It has to. If we have an outcome that it has multiple characteristics, we'll do hair color. Probability that we find brown hair plus the probability of finding some other color, meaning not brown, has to equal 1. So what we can do is do 1 minus the color that we're looking for. So 1 minus brown to figure out what our probability is of not getting brown color. So I think what I did was I switched it to shiners so that we didn't have the 0.5. Because the 0.5 was kind of confusing people since we've been working with 0.5 for the genetics. And I think this kind of clears it up a little bit. And especially also, if you do 1 minus 0.5, it just gives us 1, it gives us 0.5 again. So if we say not shiner, all right, the shiner is 0.3, all right, plus the times we're not shiners, right, has to equal 1. So 1 minus 0.3 is going to give us the probability that we don't have a shiner. Right? And this part's easy because we can clearly see, well, if we're not a shiner, then we're going to be a mosquito fish or a darter, all right, which means 0.5 plus 2 plus 0.2 gives us 0.7. We can see that. Hopefully you can see that. So what we're going to do is we have that's the probability of not being a shiner. All of our fish can't be a shiner, so we're going to have that 0.7 times our 0.7 times our 0.7 times 0.7. So 0.7 raised to the 4th, which gives us 0.24. 24% chance that we can have a collection of 4 fish and not get a shiner. Right? If we were doing not a mosquito fish, 1 minus 0.5 gives us 0.5, and then it's 0.5 times 0.5 times 0.5. Okay.
If we were to just put starter mosquito fish and then set 0.7, is that okay? Or would you
Yep,
rather
could do
just
that. Now, if you know, so you know that if all of these add to 1, that works.
Okay.
What we can't do, we can't take the probability of 4 shiners and do 1 minus that to get probability of 4 not shiners. That is not going to equal. Because all that this gives us is the probability that we didn't get all 4 shiners. This will include the probability of 0 shiners, 1 shiner, 2 shiners, and 3 shiners in our sample. So when you have a situation like this, probability of not getting something happening over 4 events, we have to look at each individual event because each individual event's independent. We have to say, well, we didn't get it on our first event, and we didn't get it on our second event. and we didn't get it on our third, and we didn't get it on our fourth. All right? You guys have questions?
Let's check these. I wonder if someone corrected me and said that it's mosquitoes. Yep. All right. Question. All right, so move this. I have a homework assignment that was posted in Blackboard. We're not going to be able to answer all of them. This will be due eventually, right? But you can notice that these first two questions are doing our probabilities that we've been working with, all right? So if you want, you can take the time later today or tomorrow to start working through these, all right? Just to kind of get extra practice or more practice doing all of these things. It's set up basically the same way, where we have this fish population and they have coloration and then markings on it. Right? So two different possibilities. And then I go through and ask about the various different probabilities. This one isn't, you're not really going to do it in R. You can use R to calculate the probabilities, but what you're going to do is do these things by hand. And for our submission, what I'll do is I will revise it so you can, so that there is a submission link that you can snap a picture or scan the answers and upload it. Or if you do it as a hard copy, you can just turn in the hard copy. I obviously would prefer a hard copy, but if you're not coming in to campus or onto campus and you wanted just to upload it, you could. But this isn't due yet. So I think on Blackboard I had like due October 4th. That was from last year. We're ahead of that. So what you're going to see is we're going to address these. And we're probably going to take Friday and probably Monday to go over these dependent events. And the dependent events, I have examples that I've pulled that were kind of relevant, but I think we can pull some real life examples now. So if you go get tested for COVID-19 and it comes back positive, what's the chance that you actually do have it? All there's a bunch of different test kits. Those data are out there. So what their accuracy, what their, I'm going to say, quote unquote accuracy is, we'll use that. Right? So if the university says, hey, you have to stay home for 14 days because you tested positive, you can work out the calculations on a back piece of paper and say, nope, Dr. N says I only have a 25% chance that I'm positive. All right, so we're going to stop here. Again, please start working through the probabilities. All right, if you have questions, email me.